My name is Ivo Rausch and it's a pleasure to me to present you one of our recent research, a PET MRI phantom study using MR-based attenuation correction to account for attenuation of the phantom material. Since now about 10 years we have PET MRI, and PET MRI provides us with functional images from PET and high spatial resolution and especially good soft tissue contrast on the anatomical side. However, MRI is not really good in visualizing solid materials, which means PET MRI, or at least the MRI part, has problems with, for example, cortical bone, hardware components, and for physicists very important also phantom housings. This issue with the phantom housings in standard MRI means that MRI is not able to account for the phantom housing in the attenuation correction, which causes attenuation correction errors. For example, what you see up here is an name image quality phantom, and depending on the system and the implementation we get up to 30% quantitative bias when using standard R-based attenuation correction procedures. A standard method to overcome this problem, which is nowadays used for phantom studies, is to use CT-based attenuation templates. The good thing of this approach is you have a correct attenuation correction. The drawbacks are you need this phantom or the CT template for each phantom, which means it's labor intensive, and usually it also needs some registration steps and specific positioning devices so that you know where exactly in the system the phantom is placed. Luckily, as of recently, there is an MRI visible polymer existing which can be 3D printed. So we thought, yes, maybe this material can also be used in PET MRI to make the MRI or the phantom housing visible. So the aim of the study is to test if a PET phantom built from 3D printable MRI visible polymer can be used in PET MRI with MRI-based attenuation correction. So what we did is we designed a PET phantom, a cylinder with some inserts. We put it into a 3D scanner, printed it, filled it with a saline water solution, and then we put it in a PET MRI and acquired a standard whole-body Dixon-based attenuation correction sequence from it and produced the standard attenuation correction. And in addition, we put it in our PET-CT to get a CT as a CT-based attenuation correction reference. Then we reconstructed the PET data with the standard Dixon-based attenuation correction, which we got from the system automatically produced. We, in addition, reconstructed the PET data with an SC consisting only of the liquid compartment to simulate a phantom where the phantom housing is not visual. And we reconstructed the PET data with a phantom-specific attenuation correction. Therefore, we generated an attenuation correction by segmenting the liquid compartment and the phantom material compartment with a thresholding approach, and assigned material-specific linear attenuation coefficients to the individual pixels. And in addition, we did the whole thing with the CT-based attenuation correction as a reference. And then we evaluated qualitative and quantitative differences between the different MRSC methods and the CT-based attenuation correction. So, to the results. What made us happy is the first result: the phantom housing was visible in the standard Dixon-based MRI sequence, what you can see here nicely in the in and the post-phase Dixon images, and also we saw some part separation of the phantom housing and the liquid material in the Dixon fat and water separation. To the different attenuation corrections, what you can see is that the standard attenuation correction treated the phantom material and the liquid compartment both as soft tissue and assigned soft tissue values, which led to an overestimation of attenuation within the liquid compartment and an underestimation of the attenuation in the phantom material. The the attenuation correction simulating the standard phantom material, which is not visible in MRI as expected, didn't show any phantom material, and therefore we had underestimations of the attenuation where phantom material was, and the phantom specific MRAC was quite similar to the CTAC, and what you can see here in the lower row and the difference image, that we just had slight deviations in linear attenuation coefficients near the borders between the liquid and the phantom housing and at the borders of the phantom. To the PET results, what you can see for the standard MRAC, visually it looks quite similar to the CT-based attenuation corrected PET, but with a quantitative global overestimation of activity values of around +9%. For the no wall or the phantom which did ignore the phantom material, we see a significant underestimation throughout the whole phantom in activity values in the PET, reconstructed PET images, and for the phantom specific MRAC, again, visually the PET image looks very similar to the CT-based PET images, and in the difference image you can see that we had almost no difference. So to conclude, PET phantoms can be built from MRI visible polymer and can be used in PET MRI with MRI-based attenuation correction. But a phantom-specific segmentation-based attenuation correction is needed to obtain a CTAC equivalent PET readings. So thank you for your attention.